average value of a function. As we talked about last time, we can use integration to try to find the average value of things like temperature functions, of velocity functions, just to figure out over a given range of independent variable, what is the average value. Now you'll remember, just from your calculating your grades, the way you take an average of something is if you have n numbers, you just add them up. y1 plus y2 plus y3 plus dot 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 plus all the way out to yn, and then you divide all of that by n. Okay? Or to write it out in summation notation, it's 1 over n sum from I equals 1 to n of y sub I. Okay? That's just an arithmetic mean, right? Sometimes I even write that as y bar when you have a given data set of y's, right? But the question now is, how do we compute an average value for a continuous function? That's when you have infinitely many values. So there's no n, there's no total number of these things that you can add up. And you don't have an n to divide by. You'd have an infinitely long series on top and a 1 over infinity out in front. Yes, sir?
Do you have any more or less?
Yes. I have 3 of them, it looks like. Nope, 2 of them. Here's one. Thank you. All right. So, for example, consider the following graph of the temperature functions, which measured in hours, and little t is measured in hour, capital T is degrees Celsius. How do we find the average value? Well, you can't add up all the different heights because there's infinitely many of them, uncountably infinitely many. One way that we could do that is to maybe take and divide this thing up into discrete intervals, and then take all of those temperatures, right, and add them up and average, okay? Then, as we typically do in calculus, take the limit, right, of how many of those subintervals that we use. So that's exactly what I'm doing down here in the next section. Consider a function y equals f of x. Divide the interval ab into n equals subintervals, each with a length delta x. Then we're going to choose points out of each one of those subintervals. So out of each one of those intervals that I've selected up here, right, I'd call that like x sub I star, and that's where I find the height of that function inside that subinterval. Okay, but you do that for every subinterval. By the way, if you do take a known length interval like AB and you divide it into n subintervals, then you've got a formula for this. Delta x. It's the length of the interval divided by the number of subintervals. That's how long each piece is going to be. And that's going to be relevant whenever I plug this into my formula and actually want to get the delta x in there. Because notice, if you take all of these xi stars, which is all the points inside of each of those subintervals, right? Maybe I could draw that a little bit better down here. I'm thinking of going from A to B, and I've divided it into subintervals equal length, and then out of each one of these, I'm picking any point inside there, and I'm calling it, that would be x1 star, x2 star, all the way out to xn star. Oh, I'm not broadcasting to your screens, am I? Do you want that? Do you care? Is that okay? Let me just a second here. There you go. Okay. Okay, and so what we really want to know is not the average value of the x's, but the average value of their function values, right? That's how we get the average value of the function. So we're going to plug in each one of those, right? x1, x2, all the way up to xn star. So our average value of the function would be approximately, and it's approximate because we've done this over discrete intervals, you take f at x1 star plus f at x2 star plus all the way out to f at xn star and divide that by how many subintervals there are. And taking the limit of that is a little bit of a problem because you've got an infinitely large sum show up on top and an infinity on bottom. So just looking at that directly, you don't see how that simplifies. But a couple things I can do here. One, I can replace n with something from this formula right there. So notice off to the side here, I'm going to say if delta x is b minus a over n, then n is the same thing as b minus a over delta x. All I did was multiply the n to this side and to divide the delta x back underneath. Right? It gives me this formula right there. So I'm going to replace that n with b minus a over delta x. And since I'm dividing now by a fraction, that becomes 1 over b minus a with a delta x on top, which I'm just going to put at the end of the sum of all these, right? F of x1 star plus f of x2 star plus all the way out to f of xn star all times delta x. I mean, really what I've got when you invert and multiply the denominator is delta x over b minus a. I just put the delta x at the end, because now what this looks like is 1 over b minus a, the sum from I equals 1 to n of f of xi star delta x. And what does that look like to you? I mean, where have we seen things that look like that before? It's area under curve. It's a Riemann sum. That's what we typically call those. But yeah, it shows up in the integral definition. So now, if we take that next step, then as always, take it to the limit. One more time. Then what you get is that the average value of the function is exactly equal to the limit as n goes to infinity of 1 over b minus a integral of the, not integral, not yet. I just want to put a limit in front of there, so I'm still doing sum. Sum I equals 1 to n f of xi star delta x. Now I'm just going to take this, since it's just a constant, and move it outside the limit. And when I do that, what I have is the exact definition of the integral. I mean, not even any kind of special form of the integral, just the integral of f of x itself. Right? As n goes to infinity. That right there is the integral from a to b of f of x dx, by definition. So booyah. That makes this right down here our formula for finding the average value of a function. It's just the length of the interval. Right, the length of the interval, or 1 over the length of the interval divided by, multiplied by integral from a to b of f of x dx. So there's really, I mean, it's not hard work to do. It's just a matter of applying it now. So let's do a couple of simple ones. If I wanted to find the average value of this function, how do we do it? Yep. So just use the formula. A and B are negative 1 and 2 now, so it's 1 over. Yep. Integral from
negative 1 to 2, 1 plus x squared dx.
So 1/3 of x plus 1/3 x cubed from -1 to 2. So that's 1/3.
1/3 x plus 1/6 x cubed. Maybe.
2 plus 8/3 minus -1 minus 1/3. 2 and 2 cubed. 2 cubed is 8. And then a -1. And then -1 cubed is -1, so -1/3.
Should it be 2/3
Where?
on the first one? Because when you distributed one, oh, you have distributed 1/3 of that.
Yeah, I've got it out.
Okay,
Gotcha.
that's where I was at.
Yeah, I just left that 1/3 out front on mine.
That makes it a heck of a lot easier.
As long as you, oh, yeah, because then you'd have to remember to put it on every single term. All right, so 2 plus 8/3 plus 1 plus 1/3. These make 9/3, which is 3, 4, 5, 6. With the 1/3 out front gives me 2. The average value of 1 plus x squared over the interval from -1 to 2 is 2. And I'm just going to graph this thing off to the side over here to get a visual that makes sense to me. 1 plus x squared is the parabola x squared shifted up 1. At -1, I mean, in fact, you can just see this. If you plug in -1 and 2, you'll see where it shows up. At -1, 1 plus 1 is a height of 2, right? I know it's going to come down to here, come back up here, and then at 2, 1 plus 2 squared is 5. 1, 2, 3, 4, 5. So the curve comes up right there. Okay. So using the information I gave you last time, when we kind of previewed this whole thing, notice now that the area that's underneath that curve, I'll do in kind of pink here. That area right there is the same as if I were to draw like a blue. Hey, come back here. Let's do a blue line. At a height of 2. All right, we're saying that's the average value of that function over that time. And as we'll mention here in a second, I'll explicitly put it in your notes, but that's meaning the same, that this area right here underneath that blue line is equal to the pink or the purple area that I had shaded to begin with, right? Those two areas are the same, which, that means this little peak up here of area matches this little valley of area down here. So they're those two shapes now have the same area. That's your average value. Okay, so it's easy to apply. There's one result out of here that I want you to know, because this theorem is important beyond the scope of just this class. It turns out to be very useful in some applications later on in this class, as well as in like a numerical analysis course that I teach, which is an applied course that some of our engineers will end up taking. It's something called the mean value theorem for integrals. It's basically saying that when you do have an average value of a function, if the function's continuous, there's somewhere in that interval where the function has to equal its average value. Right? If it's going to be continuous, it has to equal its average value somewhere. Kind of makes sense, but we can prove that mathematically that has to be the case. So think about this temperature graph, right? I'm drawing on here where the average value would show up for this blue curve. Okay, does the function ever equal its average value? Where?
12,
Yeah, close to here,
20.
right? Yeah, in this case,
That would be the end.
twice. Do what?
Would that be the integral, with the integral rows, 2 from 12 to 20,
Well, no, not really. We don't need to find an integral from 12 to 24. What I'm suggesting here is that if I did f, right, so this TAV actually, not f, that is the 1 over 24 minus 0 of the integral from 0 to 24 of the temperature curve dt. I haven't given you a formula, so you wouldn't actually be able to find it in this case. I'm just telling you, by looking at the curve, that red line is about where the height is. The question is there a little t that is somewhere on this axis, the horizontal axis, such that if I plug in that little t, I get the same value as TAVE. TAVE looks like it's about 4.8 or something like that to me, right? So I'm saying, oops, is there a place where the output, right, some number in here, gives me 4.8? And notice that's like right close to there and right close to there. There's actually two answers to that question. Okay. Now, mathematically, I'm not asking right now what are those specific values. I'm just asking, in general, if we take any function, find its average value, are we guaranteed to have that the function passes through its average value? Okay. And the one condition that makes that possible is continuity. Right? If I actually don't have a continuous function, then that might not work. In fact, let me just draw a picture for you. Okay. Let's say here's A, here's B. I have a function that does this. Where do you think the average value of that function would be?
Somewhere smack dab in the
Somewhere right here, right? That would be like my f a sub VE, okay? Notice the function never equals its average. Okay? It's kind of like saying, you know, whenever your average for this course is, say you made an 85 in this class, but you never made an 85 on any assignment. That's not so unusual, right? For averaging up discrete values, your average can be in between some of those values. On the other hand, if you had a continuous assessment of your grade, more likely a continuous measurement of temperature, right, then it would actually have to pass through that average value, right? If you looked at the high and the low and you found the average temperature on a given day, you know that the temperature at some point in the day was equal to that average, right? If you're driving from one place to another and you calculate your average speed over that distance, at some point you were driving at that average speed, right? Because the velocity of your car can't jump like that curve did right there. So there's lots of practical examples.
skip 10 degrees.
Yeah, exactly. There's a lot of examples in the real world where your measurements are going to be continuous functions, so you can know that there's some place in there where you pass through those 2 points. Okay? So the mean value theorem for integrals, which I will actually prove at the end of class, mathematically prove for you, says that if f is continuous, that's the key, then there is a number c so that f of c is equal to f of AVE, right? This really here is the key. So one of the things that you're going to be asking your homework is find the c. Find where those things are equal. Now we'll do that in the next example here. Okay? And it turns out that that's the real reason why I can make the geometric argument that I was earlier saying that the area under the curve is equal to the area under the rectangle. Because that's exactly what this line right here says, right? This, all I did to get from here to here, by the way, saying that f of c is equal to the average value, I just multiplied the b minus a to the other side. Right? And now I've got f of c times b minus a is equal to the integral. This is the area under the curve, and this is the area of the rectangle. Sorry, I misspelled that. Try that again. Rectangle that has a height of f a v e and a length of b minus a. Okay, so that's the basis of that drawing that I made up earlier on the screen, right up here. This picture right there. The area of the rectangle equals the area of the curve. The reason that is true is because of the mean value theorem. Okay? So let's do a find the c problem. So first of all, your f of x is 1 over x. All right, that's this asymptotic looking thing here. It also does it down here. But we're going from 1 to 3. We want to find the average value over that range. Okay, so FAVE would be
1 over 3 minus 1, the interval from 1 to 3, 1 over x dx.
perfect. Excuse me, 1/2 of
The natural log of x on the interval from 1 to 3.
Yeah, y'all remember that, right? 1 over x is x to the minus 1, so you can't do the add 1 and divide by it on that exponent, right? If you tried to do x to the minus 1 and integrated that, you'd get x to the 0 over 0, which is not the correct answer. That's the special formula. 1 over x is log of x. All right, so 1/2 log of 3 minus log of 1. And I made a big deal in this class about not calling it ln, right? Get in the habit, say it out loud every time you write it down. Just say log, log. I know you want to say natural log. That's fine, but it's just log. I mean, those other logs, like the common log, the log, only boneheads use those. That's just the only log you ever need is the natural log.
I think
Okay.
you gotta recognize that it's natural though. It doesn't want to be grouped in with those other logs.
If you want to give him his due cred, I mean, to me, he's log. All the rest are other logs, right? This is log.
But he's the natural one.
Right, he's natural, but if I say log, I want everyone to think this guy, because he's the guy, right? We like this guy. Those other ones, that's for clumsy, arithmeticians or accountants or scientists, not real mathematicians like us. What's natural log of 1? Log of 1? 0. So we just got 1/2 natural log of 3.
Wait, natural log or log?
Hey, I can say both.
Come on. You're changing the story now.
Okay, I'll just say log. Right? I mean, it's like his nickname, right? Everybody else shouldn't use their nickname. They're too... I'm on a first name basis with this guy.
I just give him the credit.
There you go. Log, 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 log. Now, the question is, if that's the average value, where in this interval from 1 to 3 does the function actually equal that?
Way down the line.
You think after 3? You would hope it's somewhere in between there. Mean value theorem.
It depends on what the height of what that is.
Right, so if you wanted to get a decimal number, right?
The decimal number is like 0.545.
Right, I mean, and it's somewhere between, what's the height right here? What is the height of the curve at 1? 1, because it's 1 over 1, right? And what's the height down here? 1/3, 0.333. Now 1/2 log of 3,
Give or take.
somewhere between those two. It has to be somewhere between those two.
Yeah, it's like 1.5.
545.
1/2 times natural log.
It's actually bigger than one over 3.
Yep. This is approximately 0.5493. All right. I'll round to the 4th decimal place.
That's close.
Okay? So now what I'm going to do is I'm going to set f of c equal to f AVE. F of c is 1 over c equals 1/2 natural log of 3. 1/2 log of 3. So solve for c.
So it's 1 over 1/2.
So I multiply the 2 over, I get c natural log 3, c log 3. So c is 2 over log 3. That's the formal answer, but if you wanted an approximation, that had better be where?
Somewhere.
Somewhere between 1 and 3. 2 divided by 3 log equals 1.82, roughly. Again, use as a general rule, if there are no decimals in the original problem, you need to return the closed form answer to your solution. Even though it's hard to tell, one of the disadvantages of leaving it in the closed form is you don't really know what the magnitude, the actual numerical value is. But the much more significant advantage to it is it's exact. Absolutely exact. So the longer you keep the closed form answer in there and don't approximate it, the longer your answers stay exact. So if you were to take this information and use it to answer some question as an engineer, or in some practical applied problem, you want the most accurate possible answer. So it's best to keep the perfectly exact answer in the problem as long as you can. Okay? As soon as I start rounding and start doing things with this calculation, everything I do with 0.5493 after that is only an approximation and is slightly wrong. Okay? All right, the geometric interpretation, I've already said all this. I'm just going to write it down explicitly for you in your notes, but the you can always essentially cut off the top of the mountain and fill the valley with it. Okay? Right up here fills down here. I don't know, my example broke in half here. Okay. One thing I wanted to come back, I've actually skipped over or pulled out from your homework a couple of problems that had been in there in the previous folks who have taught this class. And I just wanted to throw one back in to make sure you remembered a couple of things from when you first were introduced to integrals. There was something called the left rectangle rule and the right rectangle rule and the midpoint rule, right? Those were tools to be able to approximate the integral, right? Do you remember those, or talking about those a little bit? I mean, the idea being that if you've got a particular curve, in fact, don't draw on this just yet. I'm going to draw on this because I can erase it in just a second. But let's say I divided this interval of 1 to 12 into, 6 pieces there? 1, 2, 3, 4, 5, 6. Okay? The left rectangle rule says I can approximate the area underneath that curve, since I don't know its actual function, by drawing rectangles so that at the left endpoint of each of my intervals, I find the height, and I draw a rectangle underneath that curve for that height, right? So you'd add up this rectangle, this one, and you would get a slightly wrong, but still close answer to the area. It's wrong because of all these spaces, right? Another rule is the right-hand rule, right? Which means instead of drawing the rectangles and the heights at the right endpoints, the left endpoints, you do them at the right. So this height right here, I do the rectangle over that one by the height at the right endpoint. Okay? And it's just a numerical calculation because all you got to do is look at the picture and say, okay, what's the area of this rectangle? It's however wide this is, which is a length of 2 in this case. and it's however tall this is, which in this case is 20. 2 times 20 gives me 40. I got an area for this rectangle. And you can approximate that and add up all those rectangles, okay? So in this problem, what it asks you to do is use something called the midpoint rule, right? It says, use the midpoint rule with n is equal to 3 to estimate the average velocity of the car during the first 12 seconds. Okay? So without having a function to actually integrate, we're still going to approximate what we think the average value is. The actual value would be 1 over 12 minus 0, the integral from 0 to 12, whatever that velocity is, f of t dt. Okay? But this is what we're going to approximate. So you need to approximate using the midpoint rule. You still have the 1 over 12 out front, but now let's figure out what is the midpoint rule give us. Now, n equals 3 means how many subintervals? 3. So I take this interval from 0 to 12 and divide it into 3 equal intervals. Okay? Midpoint means I'm going to use what as the height? Or where am I going to measure the height of the rectangle? Here, 2, 6, and 10. Okay? So I have this rectangle. So the midpoint rule means all you got to do is add up the heights at all the midpoints and multiply it by your delta x. Okay, delta x is going to be 12 minus 0 over 3, or the 4, which is that length of each piece. Right? Whole interval length divided by the number of subintervals gives you your delta x. That's what I'm going to put out here. Times 4. And then I'm going to add up these 3 heights. Right? That's delta x. What's f at 2 plus f at 6 plus f at 10? F at 2 is what, 20? Plus f at 6 is 50. Are y'all following me where I'm getting these numbers? The height of the curve at the midpoints? Plus, yeah, we'll estimate that. 65, 66. 66 looks good. So this is 70 up here. It's about halfway. Okay, so 70 plus 66 times 4 divided by 12. 20 plus 50 plus 66 times 4 divided by 12. 45.3. This word also counts as license to use decimal points. Okay. And what's the units? What's the time at which the car was going its average speed?
About 5%.
45.3 is about here. Right there.
Touch over 5.
T is about 5 seconds, or maybe 5.1 or 2, right? Hard to say. Seconds. But that's the answer. What time was the instantaneous velocity equal to the average velocity? Okay?
How'd you do
I did it visually. I found where 45.3 was, right? And I drew a line straight across. I wanted to know where is the curve that high, right? What was the t value? Oops. Right, what was the horizontal axis value that corresponds with that point? So I drew this line straight down. Right, so here's 4, here's 6. So somewhere between, right, 5 is right there in the middle. So I'm estimating, right? 5, 5.1, 5.2. There'll be some tolerance in an online homework. Since we're doing this visually, the best we can do is just guess. Okay, and so I guessed where that approximately was. To me, it looks like about 5.2. I could get better guesses if I was drawing with rulers, but still, I'm limited to the fact that I'm estimating based on the values in the graph. 5 is just as correct as 5.2 from my visual guessing here. Are we good on that one? All right, so we can take this and apply this in different ways. For example, you can have a temperature curve for the temperature of a coffee that starts out at 95 degrees Celsius, just under boiling. Takes 30 minutes to cool in a room that's 60, or cool to 60 degrees in a room at room temperature. Now, one of the things we're doing right now in differential equations was we're solving for this equation. We learn how to take a differential equation and solve it so that we get the actual curve of what the temperature does in a room. We don't need to do that in here. I'm going to give you the function, and I actually give you this k value that goes into the function. The question is, what's the average temperature? If this was the temperature function, what's the average temperature of that coffee over that 30 minutes? By the way, you already know the answer has to be between what two values?
95 and 60?
It can't be higher than the temperature it started at, and it can't be lower than the temperature it ended at, right? So 95 and 60. I'm not going to work the integral all the way. I'm going to let you do that on your own. I'm just going to set it up. The average temperature T sub A, VE, would be 1 over the end time minus the start time. 30 minus 0. Integral from the start time to the end time of the temperature functions, 20 plus 75 e to the negative 0.02 t dt. You saw where I got 0.02, that's just given right here. All right, so 1 over 30 times, I do want to go ahead and write down the integral, but I'll skip all the plugging in work here in just a second. Integral of 20 is, in our case, little t, 20t. You know how to integrate 75 e to the negative 0.02 t? You can do substitution. In fact, you can actually almost eyeball this thing and know exactly what's going to happen when you do substitution. If I did substitution, let u be negative 0.02 t, and du has to be then negative 0.02 dt. What I've got to do is I've got to stick in a 0.02 negative and divide by a negative 0.02, right? So insert negative 0.02 and divide by negative 0.02. So this becomes du, and I've got then 75 over negative 0.02 e to the u. You see that? This up here is u. And the integral of e to the u is e to the u. So e to the u, which is negative 0.02 t. So I kind of combined some steps all in one. But that's a nice little trick. I mean, like I said, all that ends up happening is you need to have a negative 0.02 divided down here. So that, if I were to take the derivative of this and want to get what I started with, it would have to cancel with that 0.02 that's on the bottom. But you can go through the steps off to the side and actually plug in the substitution and then put the limits back in. This goes from 0 to 30. When I substitute 30 and 0 back in and then plug it all into my calculator, I got 76.4 degrees Celsius. Okay, but there was a little bit of, calculator work in here to get from plugging the 30 and the 0 in, subtracting. All right, I'm going to go jump to the next page, which meant to have that proof of mean value theorems at the top of it. Did I mess up and end up at the bottom of the previous page? Okay, so is everybody okay with that example? Just so you can see it once, I want to give you what the actual proof of this mean value theorem looks like, a reason why it's absolutely true. I mean, this is the great thing about mathematics is even though it seems reasonable that the mean values theorem for integrals is true, that it has to pass through the average value if it's continuous, in mathematics we can definitively prove absolute truth about this fact of the mean value theorem for integrals. Whereas in science, not that I have anything against scientists or anything, but their deductive reasoning is limited in the sense that it's only as true as the amount of evidence claims that it's true. But in mathematics, we don't have to keep just doing millions and millions of integrals and saying, well, it's true every time I've done it, so it must be true. That's not how it works in math. We can do it once and prove that it's going to be true for all possible cases, right? I love that. That's why I'm a math guy. Proof. Absolutely true. All right, so proof. So let's start with the conditions. Let's let f of x be continuous on that AB. Remember, that was the condition for the mean value theorem for integrals to be true. Now, there's a theorem that we've proven before. Now, I didn't prove it. Maybe Dr. Fawcett or Dr. Moore, whoever you had or in your previous class, didn't prove it. But the proof is in the textbook. So I'm going to use a couple of theorems that I'm assuming have already been proven. But they can be proved. And if you want me to do a proof of them, by all means, just let me know. And I'd be happy to do more proofs because I'm a math guy. I love proofs. I love proving things. I love the fact that I can prove things. Prove that I love the fact that I love to prove it. All right, so here's a theorem about a continuous function on a closed interval. It's called the extreme value theorem. By the extreme value theorem. I'm writing it out, but it's important enough that in the future, if I write EVT in a calculus class, you should know what that is. Extreme value theorem. Says on a closed interval, the function has a max and a min. Guaranteed. Right, you found maximums and minimums of functions using derivatives in Cal 1. But the extreme value theorem says if your function is continuous on a closed interval, then it has a max and min. Okay? There exists a little m and a capital M such that f of x, you know the backwards e? Do you know the backwards e? There exists, and this little thing right here, my little backwards epsilon, I'll actually write this out. Such that, I know all of you haven't had your proofs class, so you won't know all of my shorthand notation, so maybe I should write these words out. There exists a little m and a capital M such that f of x is between little m and capital M for, I was going to use another symbol, for every x on my interval. All x in AB. What that says is there's an upper bound and a lower bound for your function. Your function never goes higher than capital M and never goes lower than little m. It can't explode. It can't explode down. It's going to have a max and it's going to have a min. It can't even just approach one. It actually hits a max and hits a min. That's what that says. Okay. Now what I'm going to do is I'm going to integrate all three pieces of this. Integrate this, and integrate this over the interval. So integral a to b of little m dx is then less than or equal to the integral from a to b of f of x dx is less than or equal to the integral of a over b capital M dx. The two on the outside, easy to integrate. They're just constants. So that's little mx on the left and capital Mx on the right. And then when I plug in the limits b and a and subtract, what I end up with is little m times b minus a. It's less than or equal to the integral from a to b of f of x dx is less than or equal to capital M times the length of the interval. Right, because it'd be mx with b and a plugged in. mb minus ma gives you m times b minus a. Then what I do here is multiply by 1 over b minus a all the way through. So I have little m is less than or equal to 1 over b minus a, integral from a to b, f of x dx is less than or equal to capital M. This is now the average value. And actually, what's great about what I just said here is something that I've said is true, but had not proven. I had told you before that the average value had to be between the highest and the lowest value of the function, right? I even told you that up here on this one, right? The cup of coffee, the temperature, the average had to be between 95 and 60. It made perfect sense to us because it starts at 95 and goes down to 60, so it has to pass between. But this right here is a mathematical proof of that fact. The average value is going to be between the lowest value and the highest value of the original function f. That's what this right here, where's my point? Right there tells me. Okay? But the last thing that actually gets me the mean value theorem is something called the intermediate value theorem. Which, by the way, I like the extreme value theorem, but this one ranks in the top 10 of my favorite theorems of all time. The intermediate value theorem. Do you remember what the intermediate value theorem says? Probably not. I'll remind you. If a function is continuous, and you know it has one height at one place and another height at another place, then the function has to pass through every height in between. Right? To get from here to here, any value you pick in between there, the function passes through that height. Right? All you need is continuity, and that's the intermediate value theorem. Okay? By the intermediate value theorem, since the average value is between these two, there is a C in AB such that f of c passes through a point f a v e. And that is actually your proof. There exists a c in that interval. I'll come back and talk more about the intermediate value theorem more in this class. My favorite theorem that you can prove with the intermediate value theorem, by the way, is that if you go to a restaurant and you sit at a table that has 4 legs and they're all equal length legs and the floor is uneven and you sit down and it wobbles, right? You can always find an orientation that will stabilize your table by just turning it. You will turn the table. Eventually there's a place where all four legs will touch the ground. You don't have to put napkins underneath. If you turn it, as long as the legs were manufactured correctly and they're all the same length, if your ground is uneven, you can rotate it until they all four hit the ground. You can prove that using the intermediate value theorem, the wobbly table theorem.
So that one would be going
Just hope
left
it's a circular table, not a square table.
Yeah, because then you're all burning in the corners. All right, that's all I got. I'm done, so you guys can work on the homework for this section is due Monday, okay? We'll see you guys.